Okay, so I'm going to show you how a Newton per Coulomb is equal to a volt per meter. Okay? If I work backwards, a volt per meter, and I multiply it by delta E is equal to delta V over Q. So this unit is V over C. And then I divide it by the volts. If I change this, if I want to isolate what? Oh, I want to put my V in the bottom. Okay, so now I have your volts cancel out. I have joules per coulomb over a meter. And a joule is what? A joule is kilograms. Remember? Meter squared per second squared. So joules are going to cancel out. So now I have kilograms meter squared per second squared, ouch, over a coulomb over a meter. The meter is going to cancel out. Okay. Oh, and I dropped my coulomb all over a coulomb, right? So now I have kilograms meters per second squared over a coulomb. But we know that force is equal to mass times acceleration. So if I did kilograms meters per second squared over a coulomb, and I multiplied it by, what's the unit for force? Newtons. And a Newton is a kilograms meters per second squared. That's what is a Newton. I end up with a Newton coulomb. Whoops, I wrote another Newton. Okay. It's just a conversion of units. So this is in the teacher note package on Google Classroom. Okay. This here, a volt, is a joule per coulomb, right? If I was to solve for this. And then a joules per coulomb, you end up over distance, delta E is equal to, I don't have my data booklet, delta V over D. Okay. So it's just taking the formulas, and as you flip through it, you cancel out units. Let's finish the second half of these notes. Yeah, this is in the Google Classroom. Okay. All right. Let's look at this. A battery is a source of potential difference. That's why we use that symbol. So a water pump increases gravitational potential energy of water. A battery will increase the electric potential energy of a charge. Okay? So when we are looking at voltage or electric potential, it's the pushing power behind a charge. Okay? So here, if we were to look at this battery and we hooked it up to a motor, if this is the positive end and this is the negative end, so this is what our battery looks like, positive and negative, the electrons are going to flow from the positive to the they're electrons, so they're going to be attracted to the positive. They're going to end up through the battery, and on this negative end of the battery, they're going to be pushed away. So up here, where the attraction is the greatest, you're going to have low potential energy. Remember on the plates, this was positive and this was negative, and I had an electron or a negatively charged. The potential energy is the highest here, and as it gets attracted to the positive plate, it's the lowest. It has the highest kinetic energy. So same thing that we see here. An electron, as it goes through the battery, has high potential energy. It wants to not be there. But here, the electron wants to be attracted to the positive end of the battery. Okay? When we have this process of this flow of electrons like this, we have a current. So a current is the flow of the charge. And we solve it through I is equal to Q over C. Or Q over T, sorry. I being current, and current is measured as an amp or an A. Q is a coulomb, and T is measured in seconds. So we could say that an amp is equal to a coulomb per second. So it's a ratio, it's a rate. When you look at devices that you plug into a wall, there's always a current listing, and it's a rate of charge over time. Okay? Note that the charge is going to be the total charge. Yes. All right, let's look at an example. A cell phone charger runs on a current, not quite done. So a cell phone charger runs on a current of 900 milliamps. How many electrons pass through a charging cell phone if the cell phone is only plugged in the charger for 15 minutes? So when I look at the list of information, my current is 900 milliamps, and my time is 15.0 minutes. Keep in mind that amp is equal to a coulomb per second. So when we go through this, we need to make some conversions. I need to get this to an amp. I want amps and I have milliamps. There is 1,000 milliamps in 1 amp. So 0.900 amps. And in time, in 1 minute, there's 60 seconds. So I get what for a value? 900 seconds. Okay. Here's a formula that's not listed anywhere other than in this problem. So highlight this. The number of electrons can be determined by my total charge over the charge of an electron. Okay? So this is a new formula that I'm introducing you to in the middle of a problem. This is what we're being asked to find. I know the charge of an electron. The charge of an electron is what? Yep. Electron. 1.6 times 10 to the negative 19 coulombs. But I don't know my total charge. How do I find my total charge? With current, because this is always Q total over time. And I get what's my total charge. Mm-hmm. 810 coulombs. Now I can figure out how many electrons. I'm going to get what for a value? Okay. 5.06 times 10 to the 21 electrons. As soon as I see two parallel plates, I know that my distance is fixed. If the plates are 6 centimeters apart and have a potential difference between them of 75 volts, how much work is done against the electric field when the proton is moved 3 centimeters parallel to the electric field? There is a lot of information in here to unpack. Let's start by drawing it out. Two parallel plates. Okay. They are 6.0 centimeters apart, and they have a potential difference of 75 volts. Inside of it is a proton. So the electric field is going which way? Towards negative, okay? So this is electric field strength. If I throw a proton in here, if I throw a proton in there, which way is it going to go? The proton is going to go this way. Okay? Which direction is my force going to go? Which direction is the proton moving? Down. Okay, so force electric is moving down. My electric field strength is moving down. And so then when we look at this, we're going to back up a step. We're going to write down everything that we know. So we know distance is equal to 6.0 centimeters. We know the change in voltage is 75 volts. And it's asking us what is the work done when the proton is moved 3.0 centimeters parallel to the electric field. So it's going to move 3.0 centimeters. All right. Yes, we will have to. Because we were only looking at, did I keep those ones? I think because we were not using electric field, or energy, which is a joule. If we were just using electric field and the volt was like 6, electric field was 6 volts per meter or centimeter, and the distance was in meters, then the volts is fine. But when we switched over to energy, then we have to convert because joules is kilograms meters squared per second squared. Time has to be converted. Okay. Okay. So we're gonna go. There's 100 centimeters, 1 meter. So 0.06 meters. Same for this guy. 0.03 meters. All right. Way back in physics, look at that part of your data sheet. Work is equal to what? Delta E. Work is also equal to force times distance times cos theta. Okay, in this particular case, we can use either or. We can use the change in energy, 1, right? Because delta E is equal to delta V over Q, and we know that we're dealing with a proton. So Q is positive 1.6 times 10 to the negative 19 coulombs. We could also do this one because force electric over charge is equal to electric field strength, which we can calculate. Electric field strength is, what's the formula for that one? That one. Okay. So we're going to go this route because, just to prove a point, because it says it moved parallel. If I move parallel, theta is equal to what? Remember here we had, if we went this way, theta was equal to 180 degrees. If I went this way, theta was equal to 0 degrees, right? If one moved this way and one moved that way, theta was equal to 90 degrees. Okay, so theta in this particular case is 0. What is the cos of 0? Right. Cos of 0 is equal to 1. Okay? Yep. All right. So we're going to have to work up this way. So let's start with electric field strength. Right? Electric field strength, that distance has to be the total distance between the plates, not that the proton moved 3 centimeters. That's within the plates. This 6 centimeters is between the plates. How much? 1250 volts per meter. Now that I have my electric field strength, I can calculate out my electric force, my electrostatic force. How much? Sorry? Okay. Now that I have figured out my electric field strength, now I can figure out work. We've already said that cos theta is 1. So anything multiplied by 1 is that number. 2.0 times 10 to negative 16 multiplied by the distance that it moved, 0.03 meters. What unit is work measured in? Joules. Okay. So when we go back up here for 2 seconds, we say that work is equal to change in energy. It's also equal to force times distance times cos theta. And I tell you that you can use either or. The easiest one to use was force distance cos theta because we were looking for this distance. What's the extra part of the formula here that we would have needed to solve for distance? Because once we have delta E, how do we get distance when we have delta E? Actually, it wouldn't have mattered. Give me 2 seconds. Okay, so when we looked at the example that we just had where we were proton is placed between 2 parallel plates, we only looked at the charge moving parallel to the electric field. So what happens, the force and distance are parallel, so the work being done and the particle accelerates. If a particle is moving perpendicular, there's no work being done, and so then there's uniform motion. And so what happens when we have a problem that looks like this, where we have a particle that starts at rest? So the drawing shows an electron entering the left side of 2 parallel plates and exiting out at the upper right side. The initial speed coming in here is 7 times 10 to the power of 10 to the power of 6, sorry. Parallel plates are 2 centimeters long, so that's this way, and they're separated by 0.15 centimeters. Calculate the electric field strength inside the plates. What we need to remember is that as we go from, here's an electron coming in up against the negative plate, high potential energy, low kinetic energy. As it gets over here, it's got high kinetic energy and low potential energy. So EP is high here, EK is low, and EK is high there. Remember that the plates need to be told to you because there's no battery here. So the plates have to be labeled. All right. When we look at anything, we're going to break this down into 2 pieces. We're going to have this piece where it's moving this way. And then we're going to look at the piece when it's moving this way. When we look at the horizontal direction, what way is the electron moving in relation to the electric field? But when it's moving across, what is this? It's perpendicular. Which way is it moving according to the electric field strength? When it's over here, which way is it moving? This piece here. In relation to the electric field strength, right? The electric field strength is moving from the positive to the negative plate. So it's moving parallel. So the what? Because it moves away from the positive and into the negative. The electron's going to go the other way. It's coming in this way and it's moving up this way. Why is what going? Right here, it's got to be ejected. It's two plates. How do I get an electron in there? I have to inject it in there first. So it starts out parallel to the bottom plate. And then the negative plate is going to repel the electron and it's going to come up towards the positive plate. Does that make sense? Okay. All right. So when we are perpendicular, we're going to have uniform motion. There's no work being done, right? What's the cos of 90? Zero. There's no work being done, so it's uniform motion. Here, as the electron starts to be repelled from the negative plate and moves towards the positive plate, we're going to see acceleration. Okay? When I look at this diagram, this is very similar to projectile motion. Projectile motion, that's physics 20 coming back to haunt you. Okay? What only happens in the horizontal in projectile motion? There's only one formula we can use. V is equal to d over t. So over here, and the distance is what here? There you go, 0.02 meters. Time, we don't know. And what about the velocity? Yeah, 7.0 times 10 to the 6 meters per second. That's what the entrance speed is for that electron. Over here, what do we have? The distance is what? Okay, pardon me. What is the initial velocity? What, Kyle? Right? When it first enters into that plate, it's not going vertical, it's going horizontal. So there's zero initial velocity in the vertical direction. Okay? Time, well, time talks between both and acceleration. How do I figure out acceleration? Mm-hmm. Time we can get from here. Time doesn't change whether you're horizontal or vertical. So time is going to be equal to 0.02 over I don't know, looking for anyone. There you go. Once I have that piece, then I can solve for acceleration. Anything multiplied by 0 is 0. So distance is going to be equal to 1/2 at squared. A is going to be equal to 2d, 2d divided by t squared. You got it, Kyle? Okay. Shouldn't be a negative. Yes, -9. Yeah. No. No. Okay. Let's stop for 2 seconds and talk about why we're solving for acceleration. This question is asking us to find electric field strength. Okay? What are all of the ways that we can find electric field strength? Okay? What's another way to find? Okay? All right. When I look at these two choices that I have to solve for electric field strength, I know that I'm dealing with a electron, okay? And that in order to find force, I need some kind of relationship to force net. When I look at the diagram, here's my electron. My force electric is going to go which way? When I look at this picture, up. And what is going to be my opposing force? Force of gravity. So force net would be force electric minus force of gravity, or force electric plus negative force of gravity, however you want to look at it. Okay? When I look at this, force gravity is negligible, because how do I find force gravity? Mass of an electron is 9.11 times 10 to the negative 31. And gravity is, so my force gravity is 8.9 times 10 to the negative 30. Force gravity is negligible for atomic particles. Which leads me to say that force electric is equal to force net. Force net we solve by mass times acceleration. Acceleration we're solving by RD equals VIT plus 1/2 AT squared. So all we did here is we started at the bottom and are working our way up, as opposed to starting what I need and getting to that point of where I have to solve for acceleration. Okay? This is the pathway that we're following. We're just starting at acceleration here. Okay. Force net is equal to mass times acceleration. So my force net would be equal to what? I just cheated because I know that I'm not going to use that number anyways. Like 3.348 times 10 to the negative 20. 16, you're out by 4. Must be in either you did 31 minus 14 is 17. Oh, yeah. Okay. Alright. So now we can go Fe over Q. Electric field strength is directional. That's why it's got the vector symbol over top. Okay, let's go back and let's work on this practice problem.